Hello, everyone. This is Mr. Minnick. It's a beautiful day in the neighborhood. A beautiful day in the neighborhood. So won't you be mine? Won't you be mine? Won't you be my neighbor? Well, today we're starting the second half of chapter 5. The concepts in complexity are going to ramp up quite a bit. So I hope. Oh, we took the OGT. I know you took the OGT. There's no test this week, but we are going to cover Chapter 5, Section 5, so here goes. Theorems about roots of polynomials. Theorems about roots of polynomials. So it looks like in the objectives here, there's two theorems. So what's going to happen is they, whoever they are going to tell you, okay, so here's 7 plus rad 5. 7 plus rad 5. And it is a 0 or a root of a polynomial. They're going to tell you 7. I said they're going to tell you 7 plus rad 5 is a 0 of f of x. From that information, you're going to have to make an inference. You're going to have to infer something. You're going to have to assume something, and it is safe to assume it based on these theorems. Remember, theorems are mathematical facts that can be proved. Good for us, we don't have to prove them. Maybe we'll kind of look at how the proof of one of them goes. But anyway, so similar to that, they might tell you, whoever they are, they might also tell you something like this. They might say 2 minus 3i is a 0 of f of x2. So assuming we're talking about the same function here, where we're given both of these zeros, they, whoever they are, by the end of this, they will be asking you, write a polynomial f of x of least degree. Now that sounds kind of vague, it sounds kind of confusing, it kind of leaves you wondering, who are they? What are they talking about? I have no idea what they want from me. So, we probably ought to get these theorems. You might be thinking to yourself, well, I know what the degree is. The degree is 2, because there's one 0 and there's a second 0. So the least degree would be 2. So it would be f of x is x squared plus something. Well, you're wrong because you don't know these theorems yet, okay? So that's why we probably ought to go to the theorems. In fact, this polynomial function would have to be of degree 4, okay? And you'll see why in just a second. So they start off here in this section by telling you blah, 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 blah. Factoring can be challenging. What they're reminding you here is this. X squared plus 4x plus 3. When you factor it, what you're really doing is finding factors of that number on the end, okay? That's what you do when you factor. Find factors of the constant. And then when things got a little more challenging and a little more involved, and I don't know if this one factors or not, but if you had to factor that, then you'd have to throw in factors of 6 and factors of 3, okay? So this first thing they're starting off with is kind of interesting, and let me summarize it, because the way they put it, it's kind of scary. Suppose p of x is a sub n, nope, I said a sub 0, I said a sub n, a sub 0 x to the n plus plus a sub n, okay? Suppose p of x is that. Here's our first theorem. Possible rational roots of P of x are plus or minus the factors of a sub n divided by a sub 0. That's kind of confusing. Huh? I don't get it. What are they talking about? We'll write it down. We'll look at an example. Suppose P of x is a sub 0 x to the n plus blah, 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 plus a sub n. Possible rational roots of P of x are positive or negative the factors of a sub n divided by a sub 0. What? I don't get it. So here's example 1. Example 1. P of x is x cubed plus 3x squared minus 6x plus 5. All right. Let me use some symbols here to highlight stuff. A sub n, a sub n, a sub n. A sub n is the constant term, okay? And also a sub 0, a sub 0, a sub 0. So what this theorem is telling me is I need to find all the factors of a sub n. So a sub n's factors. A sub n's factors are 5's prime, so just 1 and 5. Well, that's not bad. What about a sub 0? A sub 0's factors. I said, what about a sub 0? Meant to make that blue. A sub 0's factors. Well, what is a sub 0? Well, it's 1, so it's just 1. So what they're telling us is that the possible, based on this theorem, what we're saying is that possible zeros, possible rational zeros, we got to keep in mind rational, that means they could be a fraction. Possible rational zeros, in other words, if this factored, these are what could be a 0. Possible rational zeros are as follows: plus or minus 1 and plus or minus 5. If we were to divide 1 by 1, we'd still get 1, and 5 by 1, we'd still get 1. So that particular polynomial is not very exciting. It doesn't help a whole lot. So let's look at another one. Okay. Example 2, their problem 1. Okay. So they're saying, what are possible roots, rational roots of 2x cubed minus x squared plus 2x plus 5? So again, we look at a sub n. A sub n's factors are just 1 and 5. A sub 0's factors are 1 and 2. So our possible rational zeros then, possible rational zeros then, are as follows. Now, how did I do this the last time? Yeah, plus or minus 1, plus or minus 5. So we want a sub n, their factors divided by a sub 0's factors. So we got 1 and 5. So we got plus or minus 1. And the first time here, we're dividing by 1. The next time, we're going to be dividing by 2 the next time. Okay. So we got plus or minus 1. And then we've got plus or minus 5. So those are a sub n's factors. Okay. And then we're going to have plus or minus 1 divided by 2 and plus or minus 5 divided by 2. Okay? So hopefully this example kind of helps to clear this up a little bit. We take the constant term, 5, its factors. And we can list them out because when we divide them by the factors of a sub 0 is always going to have a factor of 1. So again, the first time here, we really divided 1 by 1 and 5 by 1, but we don't need to write over 1 because they simplify. And then we need to go back and divide each of those by the other factor of a sub 0. Okay. Now they go on to tell us that, okay, if we were to look at that cubic function, if we looked at this cubic function, that cubic, it only has 1 0 and it's negative 1, but it is in that list. Okay, it is in that list. Just because they're possible doesn't mean they're going to be a zero. It just means if it factored, those would be potential factors. Okay. So let's try one more. A sub 0 here in this last one, or A sub n rather. A sub n is 8. So 8's factors are 1 and 8 and 2 and 4. And A sub 0 is 3. So we got 1 and 3. So remember what we're going to do then for these possible rational zeros. We're going to list the 1, the 2, the 4, and the 8 all divided by 1. So that's going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Now I know what you're thinking. Can't you just put a plus or minus in front of the whole list? No, don't do that. That's being lazy, and write a plus or minus on each one. Okay, it's not gonna hurt you. And then we need to come back through and divide each one of those by 3. So we'll have plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, and plus or minus 8/3. So those are all the possible rational zeros of that polynomial. Okay, that's the first idea that we're looking at today. We got a lot of ideas to get through, so hopefully that makes sense. One final thing I'd like to say before we move on from this is to avoid redundancy. Avoid redundancy. What I mean by that is if we had something like 4x to the 7th plus stuff plus 8, okay, what we would have is plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and then we'd have plus or minus 1/2, plus or minus 2/2, plus or minus 4/2, and plus or minus 8/2. And then we'd have plus or minus 1/4, and then plus or minus 2/4, and plus or minus 4/4. And I ran out of room. I know I would. And I didn't mean to draw that line on the board. So let's slide all that over. So then the last one there would be plus or minus 8/4. So avoid redundancy. 2/2, we already got that, so we wouldn't need to write that. 4/2 is 2, so we wouldn't need to write that. 8/2 is 4, we wouldn't need to write that. 1/4 is cool, it needs to be in the list. 2/4 is really a half, so we don't need that. 4/4 is really 1, and we don't need that. And 8/4 is 2, and we don't need that. So this list then would include plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus a hizzy, and plus or minus a 4th. Okay. So avoid redundancy. Hopefully that idea makes sense. If it doesn't, well, check out the video, play it back, watch it again in slow-mo. Okay. So that's the first of many theorems. It's called the rational root theorem. Okay. The rational root theorem. The rational root theorem. And again, simplified, it just says the possible rational roots are the factors of the constant divided by the factors of the leading coefficient. All right. Well, this is where the tough get going. They're telling you now you're going to be synthetically dividing. You're going to generate a list of possible zeros. And then, once you find one, you will have successfully taken a polynomial that's maybe cubic, maybe 4th degree, and broken it down into something more manageable. And then you'll apply all the stuff from chapter 4 that you learned. So, let's take a look at this example 2 they've got in store for us. They want us to actually find them. They don't want us to list the possible ones. But to start, that's a good idea. So, step 1, the possible rational roots or zeros. The possible rational roots or zeros are plus or minus 1, plus or minus 2, plus or minus 1/3, plus or minus 2/3, plus or minus 1/5, plus or minus 2/5, plus or minus 1/15, plus or minus 2/15. Okay. Wow, that's a lot. So once we list the possible ones, then we're about to synthetically divide. So here we go. We got 15, negative 32, 3, and 2. And we want to try, here's our first attempt. We're going to try 1. Okay, so we put a 1 in the box. And we go 15 and 15, and that's negative 17. And don't, whatever you do, don't mess up here. Take your time. Be real careful when you do this, because if you mess up once, you're going to do way too much work. We get negative 17, we get negative 14, we get negative 14, and we get not 0. Okay? So that makes us pretty disappointed. We're sad because that didn't work out. So guess what? We know that positive 1 isn't one of the rational zeros of this cubic function. You know what that means? We try again. So let's try negative 1. So we put a negative 1 in the box. And we have a 15 and a negative 32. And a 3 and a 2 and a line and a 15 and a negative 15 and a negative 47 and a 47 and a 50 and a negative 50 and again not 0. And again we're kind of sad. This is really frustrating. If at first you don't succeed, try it. Try again. It's not negative 1 either. Really frustrating. One thing interesting happens when we tried the negative 1. The signs, the SIG and S, the signs alternated here. The sign was positive. The sign here was positive, and then negative, and then positive, and then negative. Because of that, I know something. Maybe I'll share that information with you, maybe I won't. Okay, why wouldn't you? Well, I don't know. I don't know if you're ready for it today. If we have time in class, ask me to pause the video and I'll share that information with you. Okay. So I got to keep on going. Let me try 2. So I put a 2 in a box. And I got a 15 and a negative 32 and a 3 and a 2. How long do we have to do this? Well, until you find a rational 0. So we go 15, 30, negative 2, negative 4, negative 1, negative 2, 0. Yes! We got one. All right. So, what that means then is our polynomial that was cubic, 15x cubed, let me rewrite this, 15x cubed minus 32x squared plus 3x plus 2 can really be written as x minus 2 times the quantity of whatever my quotient is. So my quotient is right here, right? So that's going to be 15x squared minus 2x minus 1. So in the end, they want to know what all the zeros are. They want to know what all the roots are. Well, the zeros, one of them we said was 2. We know there should be 3 because of the fundamental theorem of algebra. And the other one, we should be able to take this. We should be able to take this and factor that. And if you can't, I'm sorry. Go back to your chapter 4 notes and look them over. Okay? 5x, 3x, 1, 1, minus here, plus there. So that'll do it. So then our other zeros are going to be negative 1/5 and positive 1/3. Okay? Interesting story. Another way you could have approached this is you could have taken this binomial, and if you plugged a negative 1/5 into a box and you divided that, believe it or not, you'll get a 0 remainder again. Watch, you get 15, and you get negative 3, and you get negative 5, and you get positive 1, and you get 0. Which leaves what then? It leaves 15x minus 5 as another factor. which would give you this 0 over here. So it all works, it all fits together. The point is, we started with a cubic. Once you get it down to a quadratic, I do expect you to be able to factor quadratics if they factor. And in this case, this quadratic right here did factor. Okay? So that particular problem asked us for the rational roots of that, and we found them. Okay? 2, -1/5, and +1/3. Wow, I feel like I just ran a marathon. So if you think this gets any easier, well, you better think again. Because that was a cubic. Sometimes there's going to be 4th degree functions. So we saw how to do one of those. Let's look at a couple of these theorems. Okay, there's one theorem called the complex. No, it's the conjugate root theorem, and it's for I don't know. Blah, 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 blah. The conjugate root theorem. They kind of put 2 parts to this. Okay, so let me summarize this on this next page. Irrational conjugate theorem. This is a very, very simplified version of this. It goes like this. If A plus rad B is a 0, comma, then so is A minus rad B. A plus rad B and A minus rad B are called each other's irrational conjugate. They're called each other's irrational conjugate. Okay? And if we were to do something like this, and this is kind of scary, the algebra involved, so don't let the algebra scare you. If we had x minus the group of A plus rad B times x plus A minus rad B like that, and we were to multiply this out, some interesting stuff happens, and actually I think this kind of helps explain some stuff. So this would be x minus A, the quantity, minus rad B, times x plus A, did that help me any? Maybe that didn't help me. X plus A, and then that quantity minus rad B. No, I guess that helped. What am I doing? Why did I do that? Why did I go down this rabbit trail? Maybe I don't need to. Maybe I shouldn't go there. Well, let's see what happens. Let's keep on trucking with this. So the first product from foiling would be multiplying this thing by this thing. That's going to be x squared minus A. And then the outer product would be x minus A, the quantity, times negative rad B. So that's x minus A, the quantity, times, that's negative x minus A times rad B. Okay? And then the inner part of foiling would be negative x plus A times rad B. And I think I messed a sign up somewhere. Oh, yeah, this over here. I knew something didn't look right. That's a minus, which is going to make this a minus, which is going to make this first term x minus A, that quantity squared. Okay. And then it's going to make this blue one over here x minus A. So let's see. And then that's going to make that a plus over there. So with that outer one, that's actually going to be a plus, and these two cancel. That's what happens. There we go. And then it's going to be on the end minus rad b squared, which is just going to be minus b. So it's x squared minus 2ax plus a squared minus b. Okay. Anyway, and all the radicals kind of go away. Anyway, the point is that theorem needs to be applied. Okay. I really should have done that with the complex conjugates, and I'm sorry for wasting a minute of your time there. This next one's called the complex conjugate theorem. Complex conjugate theorem. Conjugate. I can spell today. The complex conjugate theorem. And it goes like this. It says, if a plus bi is a 0, comma, then so is a minus bi. If a plus bi is a 0, then so is a minus bi. So if someone says 3 plus 4i is a 0, then what you can safely conclude is then 3 minus 4i is 2. Okay. So a while back, we mentioned that if you multiply a complex number by its conjugate, all the I stuff kind of goes away, and you get a squared plus b squared. And it's kind of like a sum of two squares instead of a difference of two squares, even though no such thing as a sum of two squares exists. But anyway, let's just go right in and let's take a look at an example of one of these, because you're probably like, what is he talking about? So problem 3. This is kind of like the opening example I showed you. They say rad 2 is a 0. And they also say 1 plus I is a 0. Well, rad 2 is irrational. And because of that, we need to apply the irrational conjugate theorem. So negative rad 2 is also a 0, or root. Okay? When we look at this 1 plus I, 1 minus I is also a 0, or also a root. So they're saying a quartic polynomial has rational coefficients. They're giving us one of the zeros. They're giving us another one. They want to know what the other two are. Well, we just answered that question. There we go. There's the answer. Negative rad 2 and 1 minus I. That's not so bad. Got it. Says a cubic has 3 minus 2i as 1 0, and then 5 halves. So if we look at 5 halves is rational. There's no such thing as a rational conjugate theorem. It's the irrational conjugate theorem. So, but since 3 minus 2i is a 0, 3 plus 2i is also a root or 0. Okay. So let's try another one. See what else they got going on for us. Ooh, this one's tricky. What is a third degree polynomial with rational that has roots of negative 4 and 2i? So it's going to be p of x is x plus 4 times x minus 2i times what? I know what you're saying. You're saying, well, why'd you write x minus 2i? Well, remember the counterintuitive nature of this. If 2i is a 0, then x minus 2i is a root. Okay. So anyways, the point is the conjugate of that is negative 2i, so that'd be x minus 2i, or x plus 2i. X plus 2i. So what I'm going to do is I'm going to go ahead and FOIL that first to figure this out. So that's going to be x squared minus 2ix plus 2ix. Those cancel. That's minus 4i squared. That's minus 4 times negative 1, which is plus 4. Ooh, so that's x plus 4 times x squared plus 4. So that's x cubed plus 4x squared plus 4x plus 16, and that one would be number C. Okay. For the got it, they want you to write a quartic polynomial given these roots. 2 minus 3i. So what you'd have to do is take p of x is x minus the quantity 2 minus 3i. That's one of your factors. Another one of the factors would be, because of the complex conjugate theorem, x minus the quantity of 2 plus 3i. And then because of the other given zeros, the other factors would be x minus 8. And then the last one would be x minus 2. And you got a lot of work for you to do. Real quick, let me just kind of show you how to set this up. So multiplying this, I would take x minus 2 plus 3i. And then multiply that by x minus 2 minus 3i. Okay, and then I'll just say that this is stuff here. And what ends up happening is you get plus 3i times x minus 2 minus 3i times x minus 2. So some of that stuff, that inner and outer, kind of drops out and goes away. Okay. So hopefully you kind of caught that. Now, I mentioned that the ideas here would get exponentially more difficult. DesCartes' rule of signs. Oh no. We'll probably have to talk about this again on the next day of class. Descartes' law of signs says, however many sign changes there are for f of x or p of x, then the number of positive real roots of p of x is equal to that or less than that by an even number. What the heck's he talking about? So let's look at a function p of x. P of x is 6x to the 5th minus 4x to the 4th plus 2x cubed minus x squared minus x minus 1. Okay? What we're interested in here is SIGN sign changes. Sign changes. Sign changes. So this first term is positive, then it's negative, then it's positive, then it's negative, and negative, and negative. So we want to count how many sign changes are happening here. So from positive to negative, that's one sign change. Negative to positive, that's a second sign change. Positive to negative is a third sign change. It's still negative, there's still 3 sign changes. It's still negative, there's still 3 sign changes. What they're saying is p of x has either 3 or 3 minus 2, less than that by an even number, or 1 positive real root. Okay. Here's where this gets tricky. And you might want to check this out, slow motion, play it back. Here's where it gets tricky. P of negative x would be 6 times negative x, the quantity to the 5th, minus 4 times negative x, the quantity to the 4th, plus 2 times negative x, the quantity cubed, minus negative x squared, minus negative x minus 1. And we have to simplify this, and this step here is what people don't like to do. So when we simplify it, that's going to be negative 6x to the 5th. Negative x to the 4th is going to be positive, but there's a negative out front, so it's still negative 4x to the 4th. A negative x cubed is going to be negative, so that's going to be minus 2x cubed. When we square negative, it's positive, but there's a negative out front, so it's still negative x squared. Minus a minus is plus, so that's plus x, and then minus 1. So again, we're after SIGN sign changes. Sign changes. It's negative, it's negative, it's negative, it's negative, it's positive, and it's negative. So there's no sign changes. There's no sign changes. There's none. There's 1. There's 2. 2 sign changes. So what this means then is that P of x has either 2 or less than that by an even number, either 2 or 0, negative real roots. So we would make a table. Make a table. Positive, negative, imaginary. Positive, negative, and imaginary. We said a minute ago that it could have 3 positive roots. Said that it could have 3 positive roots and 2 negative roots. In that case, it would have no imaginary. Remember what the sum's got to be because of the fundamental theorem of algebra. The sum has always got to be 5. Well, we said maybe it does have 3 positive roots. Maybe it has no negative roots. If that's the case, how many imaginary roots would it have to have? The sum's got to be 5, so this would be 2. Okay. Maybe we said it's possible to have 1 positive real root. So let's look at that. If we had 1 positive real root, 2 negative real roots, there would have to be 2 imaginary roots, and again, the total's 5. Maybe there's 1 positive real root, maybe there's no negative real roots. That means there would be 4 imaginary real roots, and the total would have to be 5. That is called DesCartes' rule of signs. Again, the trickiest part about that is right here. This is where people don't like this. They don't want to find p of negative x, okay, and look at the sign changes there. You do have to simplify that. If you don't, then you're not doing this particular law or rule any justice. Okay, that's the way it works. So if we look at problem 5, we got positive, negative, positive. There's 1, 2. 2 sign changes. So positive, negative, imaginary. It's possible that there could be 2 or 0 positive real zeros. So on this one, the hard part, again, is finding p of negative x. That's negative x. I said that's negative x. Negative x cubed minus negative x squared plus 1. That's negative x cubed minus x squared plus 1. There's 1 sign change there. So maybe it's 2, 1, and 0, or 0, 1, and 2. And there we go. I think that does it. Got a worksheet for you to try. If you have any questions, please ask. That's why I'm here, to answer your questions. If this went way too fast, I'm going to do my very best to get it up on YouTube. It's been fun. Hope it's been real fun. Have a great day.